Okay, well, thank you very much. It's a pleasure to be here. Brad did a fantastic job describing the last few years of salinity change on the Great Salt Lake and the response of the ecosystem to that, and also setting up an example of the intersection of science and effective management on the lake. And for my presentation, I'd like to provide just one interesting example of that intersection, and that's the adaptive management of salinity in Great Salt Lake. So to start out the presentation, we'll do a brief overview of Great Salt Lake structure and hydrodynamics because it's necessary to understand how and why salt moves across the lake. We'll go into a change in the largest causeway on the Great Salt Lake and how that led to a rapid export of salt from the Artemia producing arm of the lake, a gradual but concerning return of that salt back to the Artemia producing arm and rising salinities, how that led to an adaptive management action on a brand new causeway berm on the lake, and how that adaptive management action directly resulted in the export of salt back out of the Artemia producing arm of the lake. So as Brad mentioned, the natural condition of the Great Salt Lake is one large open basin, but in 1959 a railroad causeway was built across the lake dividing it into north and south arms. Now, an important thing to realize is that all three rivers feeding Great Salt Lake enter to the south of that causeway, into the south arm. And that's important because only two small culverts provided any connection between the two arms, and they were not large enough to promote the full mixing of the two arms of the lake. And what that means is that the south arm, where the Artemia are generally produced, tends to export salt north into the north arm. The north arm tends to retain most of that salt, and as a result, the salinity of the south arm tends to range between about 100 and 185 grams per liter, and it supports the Artemia food web. Whereas in the north arm, salinities tend to be at or near saturation, and Artemia production is minimal most years in that arm. Now, the flow through the culverts of the causeway is stratified, and is bidirectional, and is driven by differences in density and surface elevation between the north and the south arms. So the south arm is lower density water, and as a result, it tends to flow on top of the higher density water as it enters the north arm and mixes in. Whereas the high density saturated north arm water sinks and flows along the bottom of the culverts, entering the south arm, and this high density layer doesn't mix very easily, so it will often form this monolimnion, this deep brine layer as we call it, that will spread across the bottom of the south arm and gradually release salt up into the upper water layers. So this is essentially the conveyor belt of salt movement through the lake. Dense brine from the north arm pools at the bottom of the south arm. It will gradually mix its way up into the upper water layers of the south arm where the Artemia food web is. And that's why the south arm remains saline, even though it receives all three inflowing rivers and sends some of its water into the north arm, is you get this return flow of heavy brine from the north arm back into the south. Now, the culverts began to fail in 2012, and that structural failure of the culverts was a threat to the railroad line on top of them. So in 2012 and 2013, the Union Pacific Railroad decided to seal up those causeways so it wouldn't collapse and take out the railroad track. And the result of that was the connection between the bays of the lake was greatly reduced. That anoxic deep brine layer in the south arm that was fed by the north arm was cut off from return flow from the north arm. And as a result, it gradually dissolved up into the epilimnion. And because there's less water able to head into the north arm from the south arm surface elevation rose about 1 meter above that of the north arm by 2016. However, a new bridge and opening in the causeway were built and finished in December of 2016 to reconnect the two lake arms. Now, this bridge was about 55 meters wide, and unlike the culverts that came before it, it extended from the lake surface down to the lake bed. And you can see in this picture here that the remaining part of the causeway is holding back the green waters of the north arm, which are at a higher surface elevation than the pink arm, the pink water of the north arm in the foreground. And so that dam was breached within a single day in December of 2016. And what that did is it released a massive flow of water one way from the south arm into the north arm. And this flow lasted for about 5 months straight, the first 5 months of 2017. The first 2 months of those were caused by the hydraulic head that had built up. The next 3 months of that one-way flow happened because 2017 was a year of above average snowpack, and so the river inflow was very high entering the south arm, continuing that hydraulic forcing of south arm water into the north arm. So the graph we can see here, when the one-way flow initially started, it was about 5,000 cubic feet per second flowing through that breach. And after about 2 months, that declined as the head difference between the two arms started to stabilize. This blue line represents the river inflow to the lake from the snowmelt. And as that started, the one-way flow from the south to the north picked up again, reaching about 4,000 cubic feet per second and continuing on for several more months. The practical result of that is that it was a lot of water moving into the north, and it was also a lot of salt, as we'll see later in the next few slides. Another practical result is that this lowered the salinity within the south arm by a substantial margin, and it did so for the next 3 or 4 years. So between 2017 and 2020, salinities in the south arm were down to about 100 to 130 grams per liter, and that's a very healthy range for the Artemia population. However, in 2020, we started noticing from our monitoring program that the salinities were starting to creep up again, and doing so in a way that was disproportionate to lake volume changes. 2020 was the start of the dry cycle that Brad talked about in the last presentation. And in 2021, these salinity increases were worse than they were in 2020. And we started to get a little bit suspicious and wondering what was going on with this change. And we suspected that a lot of salt had been moved north when the causeway breach was opened. So what we did is we took our long-term salinity monitoring data from our program and we plotted it against the lake surface elevation for key time periods. So for the 7 years preceding the opening of the causeway breach, we had this nice linear relationship between the surface elevation of the lake on the x-axis and the salinity of the upper water column on the y-axis. And that would seem to indicate a fairly stable salt mass within the south arm that is just being diluted or concentrated as the lake naturally moves up and down with evaporation and river inflow. However, when we plot the data after the causeway breach was opened, we get a different relationship. This is 2017 to the middle of 2019. And we can see a very similar slope to the relationship, but for any given lake elevation, the salinity is about 20 grams per liter less, and that's substantial. If we plot the data where we saw salinity increases after this from 2020 to 2021, we see the relationship change again. Now the slope has gotten steeper, and the data points are starting to return back to that old relationship before the salt was moved to the north. And not only that, because these were dry years, by the end of 2021, the salinity in the south arm had now reached about 170 grams per liter. And that was starting to be concerning to us because we still had that open causeway breach with unrestricted heavy brine return flow into the south arm. And we weren't sure where this pattern was going to stop. But we needed some more concrete direct evidence that it was actually the salt mass in the south arm changing and not just salinities. So we have 9 routine monitoring sites on the lake. And for this, we chose our 2 deepest sites, shown here in the red points, that enable us to sample the entire depth of the water column down to the bottom of the lake. And that's important because some years with a heavy brine layer, you have some substantial density stratification down there. And so we mined our data, and we took the salinities that were measured at 1, 3, and 5 meters in the upper water column, and that resolution started to increase as we got down towards the bottom, sometimes 5.5, 6, 7.5 meters, trying to get a good picture of salinities in the water column. And it occurred to us that because the United States Geological Survey, which produced this map, has a good bathymetry data set that can give us the volume of the south arm of the lake at a given lake elevation, we could use this data to calculate salt mass. So for each one of these sampling elevations, you could pair that to a volume within that layer of the lake. Multiplying salinity by volume gives us mass of salt. And we did this exercise for about 90 individual sampling dates running between 2016, 6 months before the breach was opened, and late 2021, which is where we started becoming very concerned about salinity. And this gave us a 5-year time series to examine. And when we examine that time series, we see that our suspicions that salt mass had moved during this time period were confirmed. So on the y-axis here is salt mass calculated for the south arm in tons, and on the x-axis is the timeline from the middle of 2016 through to the end of 2021. And the breach was opened here at the end of 2016. And we can see that nearly 20% of the salt was exported north to the north arm during that time period of 5 months of one-way flow. Salt mass started to creep back into the south arm as return flow resumed in later years, but this was gradual until the slope steepened in 2020 and 2021 when we started seeing those concerning rises in salinity. And by the end of 2021, most of the salt that had been exported into the north arm had returned to the south arm, and that was a bit of a problem because this was a dry year, resulting in higher salinities than we'd like to see. Okay, now fortunately, Great Salt Lake has a lot of engaged and effective stakeholders for managing the lake. They range from the legislative to state and federal agencies, private enterprise, and university researchers across a number of different fields. And one of them in particular is the Salinity Advisory Committee, and this is one that Brad mentioned in his presentation. It's a group of experts that advises the state agency that manages the causeway and the causeway berm on salinity issues and provides advice on what changes could be made to provide effective adaptive management and keep salinities within a healthy ecological range in the south arm. And what this means is that we had a place to bring our concerns about salinity and salt movement that we had found. And so we did so. In the fall of 2021, we brought these results to the Salinity Advisory Committee, and they hadn't noticed this change in the lake. We were the first ones to have seen it, and so this interested them, and they wanted it verified, and so they asked their government scientists to verify our findings using their own data set, and they found the same result as we did. And so the committee recommended halting return flow of that heavy brine from the north arm. And the way to do that is by the adaptive management berm that was built into this new causeway structure. And what it simply is a raised portion of fill that can be raised or lowered by adding or taking away fill in order to modulate the amount of bidirectional flow that comes through that breach. And so what they did is they worked with the state agency, secured funding, and the state agency approved the change to make this modification. And so the berm was raised in 2022 simply by adding more rock fill to it. And it was raised to an elevation that university hydrodynamic modeling suggested would halt that return flow of heavy brine from the north arm. Okay, and it was raised again in 2023 because we had that record high snowpack that Brad talked about, and they wanted to retain that inflowing water into the south arm, allow it to mix fully with the salt before flowing over into the north arm so it would maximize the export of salt out of the south arm. And so a quick demonstration of how this would work. With the breach entirely open, you have unrestricted bidirectional flow. If you raise the berm modestly, you can reduce some of that heavy brine return flow. If you raise it more, you can block just about all of that heavy brine return flow while still allowing the flow to go from the south to the north and keep exporting water into the north arm. And this is the modification that was done in 2022. In 2023, it was raised again to completely block off return flow and to limit the amount of flow going back into the north arm until the lake rises. And an emergency option that's on the table due to some new legislation at the state level is that if the lake drops below minimum elevation, they can raise the berm to completely seal off the two arms until the lake receives enough water to go back up. A quick view of some pictures of what this looks like. This is, on the left, the breach before the adaptive management berm was raised, showing unrestricted flow both directions. And on the right, this was after the modification made in 2023, completely blocking off return flow from the north arm, but allowing the south arm to export salt to the north, which is the intent. And we've had really effective results over the last 2 years from these modifications. So if we extend that salt mass time series now beyond where we initially raised our concerns in 2021 to where the berm was raised in 2022 and again in 2023, we can see that the salt mass within the south arm is again going back down and has dropped below the level it was in 2017. And so current salinities now are about 116 grams per liter in the lake, which is excellent. And so what this has effectively done is it's lowered the lake elevations at which the healthy salinity range for Artemia can be achieved. And so the tolerance range of Artemia, as we mentioned, is between 100 and 180 grams per liter. That's shown in the blue band on this graph, the range of salinity. And on the x-axis is the lake surface elevation. Each of these lines represents the elevation at which these salinities are met, given a certain salt mass left in the lake. And so this dotted orange line is the peak salt mass that we measured in 2021. And the solid orange one is the salt mass that existed in the fall of 2022 during the lowest point of the lake. And then again in the summer of 2024 where the salt mass currently rests. And what we can see is that at any given south arm surface elevation, the salinity is lower than it was several years ago. And what that also means is that if the lake does hit that low phase that we talked about in 21 and 22, instead of salinities being up near 180 grams per liter, they'll now be closer to about 165. And that's an important change because it brings it back within that tolerance range of Artemia, and also because climate forecasts for the American West suggest that drier conditions, like we've seen over the past 20 years, are more likely to be the case in the future than the few periods of really wet years that have been so popular to cite from the 1980s and the 1990s. And so what that means is that the lake salt mass right now is currently set up for the lake to be able to handle drought better than it would have before and still provide salinity ranges in the south arm that will support the Artemia ecosystem. Okay, so the Great Salt Lake is actually quite fortunate. By sheer luck of geography, we have a causeway that goes across half the lake, and all of the inflowing rivers enter into the south of it. And so what that means is that more than half of the lake is able to be protected and have the salinity actively managed through this adaptive management scenario. And that's not something that other saline lakes that are facing the issues of increased water use and drought are able to do. Additionally, we have a lot of long-term monitoring data sets on ecology, hydrology, and salinity, and we have that active group of informed stakeholders that can use that information to make, hopefully, correct salinity management for the future. And so the lake is set up to do as well as it can in the future. We've got a strong management structure, a lot of actively engaged stakeholders, and a lot of really good science going on in the background that can support this. And just one example that I think people working on the lake are particularly proud of is that this cooperative management structure that we have was part of the reason why last year the lake earned the Marine Stewardship Council's Certified Sustainable Wild Fishery Certification, which is the first U.S. inland fishery to receive this and the first Artemia fishery in the world. And so we're optimistic about the future of Great Salt Lake, and we're excited about this adaptive salinity management that has occurred over the last few years that seems to really be beneficial for the lake. So thank you.
Thank you, Phil. Wonderful presentation, and showing now the element of how the engineers can come in next to the biologists, next to the policymakers. Very good example on how the future of the Great Salt Lake is really taken care of.